Yes, thank you. And it's a real pleasure to follow this fantastic talk of Amaury. So also one more thing, this year I'm actually mainly visiting the École Normale, the wonderful Center for Sciences de Données, the Center for Data Science there. All right, so my topic is, now Amaury forced me to kind of choose, is it for or, what was it? For math or, what was the other thing? By. I'm going to try to address both, but it maybe started out more with the, we did the math to say something about large language models, but I think we might be able to now have some insights also about math and in particular the usage of synthetic data. All right, without further ado, this talk is based on work with my wonderful collaborators, Elvis, who is not here, my student Yunchen, who is somewhere here, there. Of course, François, who probably is on the paper of every talk in this session, in this workshop, and another student, Pooh. And I will, in fact, I secretly added another slide in the end about work that we also submitted yesterday at 10:30 p.m., which is not yet featured here, but I'll mention it because it might have some relevance. All right, so to set the ground, as Amaury already said, the world has significantly changed, at least for us in our AI bubble, with the advent of these large language models, also large image models, video, etc. And we approaching something which we called, we meaning us, locally our co-author group, as the synthetic data age. So what does it mean? We asked ChatGPT, what does it mean? And this is what ChatGPT said. And then Yunchen asked GPT to produce this picture. And it's all a bit gibberish, although it looks very nice. And what I found particularly noteworthy on this picture is that when we ask, what is this? This is the question in our paper that we say, what happens when data enters the training corpora of the next model? So we ask this to GPT and he produces this, or they or she, now it doesn't work anymore, produces this picture, which, as you know, as you might notice, is full of gibberish. I mean, if you look, it looks kind of right, but it kind of there in the business model. So this is very telling for the story I want to tell in the next few slides. And I will start by mentioning some empirical and also theoretical observations that people have made over the last maybe 3-4 years, 2020, when they started training larger and larger models. They had kind of two knobs to tune. On one hand side, you could increase the parameters of these models. And you all know that we are now in the, I would say, we're approaching the hundreds of billions, or we are in the hundreds of billions of parameter range for the models. And at the same time, we have data which is in the trillions right now of, say, tokens, or even more. And so we have these two massive things that we can tune. And how does performance of the model scale with these two knobs? And you see here, there is an empirical paper by Kaplan and others, which shows the loss, so a metric of how good the model, in this case, it was language models, I believe, the loss as a function of these two parameters, the data set size or the parameter size. And you see this is a log scale, on the x-axis at least. And you can see that there are these kind of linear curves emerging that then saturate eventually. But as you increase the models, there are these curves. And so people started empirically writing down these scaling laws, which c'est censé de marcher. But anyway, there are the scaling laws that you can see empirically established, which basically show how the loss scales as a power law in the size of the data set, which is T, or in the number of parameters, which we call D. And this is something that, was observed in around 2020, and not only by this paper, but by several other papers. And then there are a good amount of theoretical works proving that in various models, indeed, there are scaling laws. But the main point is that they're being used in some sense. They're used in order also to understand how to trade off, for instance, parameters versus data. So you can draw these kind of isoflop curves where you kind of have some sort of currency. One data costs me as much as whatever, 2 parameters or whatever it is. And you can kind of find the sweet spot where you know what trade-off to have between data and size of the model. And there are various, works that show various of these trade-offs. But when people nowadays build larger and larger model, in particular, they are in a mindset where they know we have to be bigger in the model and we have to have way, way more data, and we believe we know how it scales. And these are these scaling laws. One more thing is that these scaling laws also have been related, which in some very vague sense is called the emergence of skills in these models. For instance, there is this paper here, Emergent Abilities of Large Language Models, a couple of years ago, where people observed that as we scale the model size or the data sets, in this case, I think the X, this is training flops. So it's some sort of model size with normalized with data. As we kind of increase these things, parameters and data, certain skills start to emerge. And there's a bit of a discourse in the community whether they emerge abruptly or whether they emerge gently. It's irrelevant. It depends a little bit on the metric. But the point is, there's also this perception in the community that as you increase your data set size, the thing starts to be able to do things it couldn't do with smaller sizes or smaller data sets. And we have, of course, François Charton here prominently. We demonstrate these skills that are learned also on a very simple example of a transformer, which learns to predict the greatest common divisor. So it gets two numbers A and B, and it's supposed to tell us what's the greatest GCD of A and B. And what you see on this graph is as we increase the training set size, so we give it more and more examples of learning GCD, it starts to learn various combinations of GCDs. For instance, the green one, so this is in a particular base, this is modulus something. So it's a bit idiosyncratic, but for instance, the green curve, so it relatively quickly learns to predict 3 as a common divisor because of the choice of base, which I actually forgot what it is here. Maybe François remembers. And then later it learns to predict, 2 and 6 and 34, and so on and so forth. And then, eventually, as it has more and more data, it learns more and more of these skills.
The base is 2023.
Okay, the base is 2023, which was chosen because it is nicely, it's not prime, but it's nicely factors into 34, I believe, and something else. Anyway, whatever it is, the point is it learns these various skills relatively abruptly as we increase the size of the data set. And there is one more point I want to make about these scaling laws. They are empirical, but when people try to prove them, all the proofs I'm aware of that have this scaling behavior in the size of the data set use the assumption that the data that you feed to the model is never uniform. It has always some sort of zip law-like structure. This is true for language. As you know, the whole zip law was, I think, established on some, observed as frequency of words, frequencies of letters. It is generally true, I believe, for any text corpus that you might want to think about. But in particular, it's very acutely true for the greatest common divisor. If you pick two numbers at random, think of 2. Pick two numbers at random, probability that they're both divisible by 2, 1/2 is a quarter. By 3, it's 1/3, 1/3 is 1/9, etc. I mean, I'm just giving you rough heuristics why you will see a power law, a quadratic power law for GCD. So when you pick two numbers at random, here is the distribution of GCDs. And it goes with the power law. All right, and these power laws are also ubiquitous. So Zipf's law, this is War and Peace. And we have a histogram of the distribution of words. And generally it is, as I said, in all these scaling law theoretical proofs, it's assumed that the data has some sort of Zipf-like structure. All right. Having said all this, let's look at one of the bigger language models that are currently available. Llama 7b or Mistral 7b. You heard about Mistral, that's the defection from math to language models that Amaury mentioned. When you look at the data, and now I'm becoming a little more vague, less mathematical, but when you look and do some sort of histogram of the data, now we do not count the frequency, we just look at the perplexity. So some notion of how likely the language model thinks a certain text is. And here we use some sort of wiki data. When you measure perplexity, you also see this kind of zip law distribution in the language model. And I'm putting it there with some kind of, without saying much about it. The point is, okay, so now let me give you one proof of a scaling law, the simplest one that I know, which kind of nearly fits into one line. So why do our models scale in this inverse power law with the size of the data set. Here is the simplest model. It was analyzed by Marcos Hutter in 21. It's a model that has infinite memory. So what does it mean? Here is data that comes from a zip law distribution. So the probability that you get some, say, number, let's say integers, that you get some number I, scales with inversely with the power, I to the minus beta. And we're given an IID data set with some label for each of these. And these are, say, our tokens. And what the Hutter model does, so the infinite memory model, if it sees some datum, it will remember it, including its label. And if it doesn't see it, it will always output, I don't know. Okay, so infinite memory. If I've seen it, I know it. And if I haven't seen it, I don't know it. Okay, very simple. And how do we measure when it's correct? Oops, sorry. So when is the thing wrong on a test point? So it has seen a lot of things. It has seen T data. And now it gets a test point I, which comes to it with probability P of I, which is this inverse power law. And it will be correct if it has seen this point I. So it will be wrong if it hasn't seen the point I. And it hasn't seen the point I if it has received T points with probability 1 minus Pi to the power T. Right? That's a probability in his training data set of size T. It hasn't seen this point. And so we can write this test error in this very simple way. When you do half a line of math extra, you see that it scales inverse proportional with the size of the data set to the C, and C is this 1 minus 1 over beta, the initial distribution. Okay, so this is really, I thought it was a really cute and easy proof of how the scaling laws emerge in an infinite memory. So here we don't have parameters because the thing just remembers everything. Okay, so the moral of the story here is data comes as zip, and then the test or error in some log scale goes down linearly, and you can prove this in various settings. Now, having said all this, let's step back and ask the question. We have GPT, we have diffusion models, we have a lot of generative AI in the world. Just historically, for instance, January DALL-E. Do you remember DALL-E? I mean, I think people don't use it very much, but it generates these images when you tell it what to draw. DALL-E 2, Midjourney, Stable Diffusion. So all these image models, and this goes on, of course, into our time. And just the recent language model revolution, November, a year and a half ago, ChatGPT appeared, and then we have all these other models. And in fact, at the moment, about 0.1% of all language, so 1 in 1,000 pieces of text in the world, is produced by ChatGPT. That I got this from this Sam Altman, I don't know where we got this from, but it might be overclaiming because it comes from OpenAI, this statement. But I think it is approximating some truth. So 1 in 1,000 pieces of text are generated by AI. And that's just ChatGPT. And then think of the other models that our friends are producing. So we must contend with the fact that whatever is out there in the world, on the internet or wherever, is more and more synthetically produced by some language model. Okay? And this will probably only increase. And then think about how our models are trained. What are they doing? Under the hood, everybody goes to the web, everybody scrapes that text, and then trains the model on that text, maybe with some data curation, but in the end, that's what people do. So what will happen is the model is trained on the internet, on the pristine internet from 2020, perhaps, and all is good. But then as time passes, the text pieces from these models go back to the internet, and the next model, GPT-5, is already trained on data that has stuff from GPT, the famous 0.1% of GPT-4, and so on and so forth. So we must ask what happens to our scaling laws, and generally, what is this synthetic data doing to us? And also related to Amaury, also synthetic data is used in contexts that when it's very hard to produce real data. As we have seen here, suffered tremendously to produce 1 million, 1 million Lyapunov kind of pieces of data. We're very tempted to use maybe synthetic data in the sense that why don't we train a transformer and produce even more of this data? And then train another transformer on that more data. Maybe that will get better, right? It's a natural thought. You didn't say it, but I'm putting it in your mouth nonetheless, but it's natural. All right. So what happens? And indeed, if you look at the literature, especially starting in 2023, which still is ancient in our kind of AI world, lots and lots of kind of anecdotal, empirical examples appear where they say, oh, I use the diffusion model and suddenly my classifier is much, much better. Something like this. Of these types, so this is the whole line stuff there, and we stopped. Our paper was written in November. Probably there's another 20 lines of other references that say, oh, fantastic. I used this model. It made a lot of data for me. I stuffed it into my other model, and lo and behold, I'm getting much, much better. So there's lots of this literature. It's mostly, as I said, anecdotal is maybe a little bit not nice to say, but it is empirical. Then there's a bit of critical work, which says, oh, this model that you used, this big diffusion model that generated your synthetic data that you used for your other model, had you used instead the training data of that diffusion model, you would have done much better. So in some sense, you see there's a hidden thing where the strong model that was used to improve the other model was strong because it was trained on much more data. And there are other, there are distribution shifts where it helps, etc. But one has to be very careful with these statements. Oh, it really helps when you use synthetic data, because this is the statement that we need to, we need to look at it more carefully. All right. In parallel, around a year ago, papers, or this is the first paper I know of that appeared that start to warn of what they call, or what was called in this paper, now we all call it like this, model collapse. So the curse of recursion. This is the first paper. It is a very nice paper in the sense that it observes this phenomenon. So here is the kind of abstraction. We have data, it's real data, we train a model. The model produces some data, the next model is already trained on data from the previous model and the real data and so on and so forth. And they drive this abstraction to the point where they just say, let's assume the model is trained only on the output of the previous model, just to analyze. And they look at this loop of a model producing data, having the next model trained on it, and so on. And they do some experiments and they analyze it on a simple Gaussian case. Let's see if I have it. Yes. So if you think about it in terms of sampling, and you have a Gaussian, say, and you do this process several times, what will happen is that you'll start missing the tails of that Gaussian, right? Because just simply by sampling a finite amount, you'll only sample the center, you'll retrain a model, it will learn more of the center, and as a result, this is a variation autoencoder, but kind of according to this principle, what you'll get is a narrower and narrower Gaussian until you only output one point, and the thing is totally senseless, okay? So they analyzed this. There are other papers that appeared 6 months ago, perhaps, where people did this for diffusion models, and they did some theory along these lines, but they also analyze, basically they run these diffusion model on the outputs of their own, predecessors. And you can see, it's just cute. You can see how these fully synthetic, how that face kind of degrades into something weird, or here these kind of weird textures appear. So not good. But these results basically did these loops and looked a little bit what happens. What we now ask is, what happens to our scaling laws? So I just mentioned to you, and I tried to convince you that these scaling laws are used, especially, Gabrielle is now here, in industry to guide you how much data, how much parameters, etc. And in particular, we think more data is better. So what happens to these scaling laws when we get all this synthesized stuff? And what we will show, and I'll get into, is that various effects happen. To take the message away right away is scaling laws break down. And this is our teaser figure where you see, so up there, you see that the scaling laws should have gone down with real data, and you see how it tapers off, even though you have more and more data. It's not that you run out of data. It's just that for some reason your data doesn't help anymore. And we also analyze what are actually the effects of synthesizing data when you look at the zip flaw. And the effects, also to take it away already, are that when you have zip type data, if you synthesize it, because of kind of finite sample effects or things that language models do, they usually do something called top P inference, for instance, where they only take the most likely outcomes when they generate new tokens. They don't go into the tail of the distribution. So these have the effect of cutting off the tail of these zip flaw distributions. So this is the model we start as. We model synthesized data by some cutting off effect of the tail, or by some narrowing of the tail. And we'll see how this corresponds to the truth. And then we show that as a result, these scaling laws just disappear.
Can I ask a question?
Yes.
So just want to make sure I understand. Did you say that zip flow explains the scaling laws? So zip flow is something about text, right? The scaling laws are about the transformers or the whatever.
Yeah, so I didn't say explain. I said when you look at proofs, I gave you a very simple proof for infinite, but there are of course more sophisticated proofs around, lots. all of them assume a zip distribution on something. And of course, in the abstract proofs, they assume a zip distribution. Say you have random features that the eigenspectrum of these features has a power law or something like this. But you need this as a theoretical ingredient to prove any scaling law. Let's put it this way. Does it help? Okay.
One question. Model collapse has been known for many years before LLM. I think in previous age we can use some control parameters such as cross entropy and self entropy. So we can control the diversity of the data, right? And that's one problem. Another problem is scaling law is normally based on smaller models such as Llama, but we just simply use a kind of analytic continuation, try to extend into a larger space, a larger model, a larger amount of data. But basically, my question is, our observation is derived from experiment with the smaller models. But how certain is to extend this observation into larger space?
So I don't know which order to take your question. So first of all, as you know, in this field, everybody reinvents things that have already been invented many times. And I have no doubt that, especially in the statistics literature, I have no doubt that resampling with finite sample size has been analyzed. No question. Okay, so I don't make any claims to that point. But you seem to be asking, and correct me if I'm wrong, if the scaling laws hold once you go beyond Llama 7 billion. So, of course, the theoretical proofs always hold, right? They just scale. In practice, these scaling laws that I showed on the first slides, I believe people, I mean, again, we should ask Gabriel, who's just sitting here, but and building large models. So I believe the empirics keep holding even for the large models. And in fact, these empirics inspire the next generation of very, very large models, if I'm not mistaken. But this is an empirical question, right? So you're asking me, are they measuring the scaling laws for GPT-4? I suspect they do. But these publications were at the...
Another problem is that we try to use the observation to apply to a much larger model, let's say 170 billion and even over 200 billion. But based on 7 billion Llama model, I think this could be problematic.
Of course, but I believe, okay, this is empirics, right? But I believe people indeed, they try to understand the trade-off between data set size and parameter size. Should I scale this by factor 5 and this by factor 2? Or should I scale them the same way? And there the inspiration comes from, of course, the previous model. It does see, okay, how many experiments? There's no good counterfactuals because things become very expensive once you build big models. But I believe this is the guidance when they do bigger models to look at these trade-offs. Of course, it's a valid question. Does this ratio carry over to larger models? But they have done, right? They haven't just done it on Llama 7 billion. They did it on very small models, middle-sized models, up to maybe whatever, 100 billion. And this linear curve seems to hold empirically. So now you can ask, well, assuming we double now the size again, will it hold? At least there's some evidence from various sizes, not just Llama 7 billion, right? So, is that okay? All right. Let me move forward and just give you a little bit of the math here. Right, so what we show is we start with this infinite memory model that I've shown you, and then we analyze various variants. So I'm not going to give you all these details, but what I want to point out is not only do we have these finite sample effects that make it such that we don't sample from the tails of a data distribution, but the language models seem to particularly be built in a way to cut off tails of distributions. And there's, to your point, there's quite some works that also show that they reduce diversity by various metrics. And of course, then there's control buttons. But when you face text that was generated in the wild, you cannot be sure that somebody applied some control to generate something particularly diverse, right? We don't know. Okay, and so what we can see is that these Llama models, when they produce a probability distribution over the next token, they tend to peak this distribution more. They increase what's called the temperature in order to basically only consider the top 5 choices, something like this. So they naturally cut off tails. And they also they only look at a certain, they only look at next tokens where the, say, 95% of the probability mass lies, and they peak the distribution even more for inference. And when you look at what all this happens, when you translate these effects of what these models do plus the finite sampling bias, what you get is that these tails are simply chopped off. That's what happens. And in fact, oh, let me see. What did I want to say? Right, okay, so let's assume for now, I thought we had a graph how the tails get cut. But let's assume that's the effect, that we get tail cutting of the data that is generated. Oh, here it is. So here we did this experiment with Llama at the time. The original data in this perplexity setting, where we look at this zip flow with perplexity, has a decent tail. And then when we look at one generation with various settings of these temperatures and top P, we can already see how these tails get narrower or cut off. And then we did this with Françoise Charton's transformer for GCD. We trained it on a certain data set size. I believe it was something like 200,000 samples. And then we had to generate new GCDs. So we gave it random pairs A, B and asked what is the GCD. And you see that it made guesses, but it cut off the distribution. It never guessed a GCD bigger than 120 in this case. Okay, so empirically, we also see that what happens when you stop training models with a certain data set size and then regenerate, what we do see is that these tails get cut. All right, and so what we then proved is in various models that are variant of the infinite memory model, not only, we proved that indeed what happens when you do the analysis is that your scaling laws will stop. So the original data was supposed to scale, you see, with sample size like this, the red line, and what happens when you have various cutoffs of the tail is that the scaling laws stop. And then your performance just stagnates. And then when you, that's what happened. This is the cutoff. So here are various simulations that show what happens when you cut off the data. But it's to be expected if you think about it, right? Because as the models become larger and larger, they take more and more care of this zipped tail. And when you stop training them and have them generate, they will not have that tail. And so there is no improvement, if you think of it this way. All right. Let me skip a little bit and just show you also empirical work that we did with Llama. So we had Llama regenerate data and then retrain, and I'll show you what that data was in a second. And you can see that this curve looks like nothing, but these things take weeks to generate. And poor Yunchen is still exhausted from, I think, last night's deadline of regenerating more of these curves. So this is a Llama curve, a test curve, the red one on the original data, and I'll tell you what that is. And the blue one is when we have generated data from the previous model. All right. Let's go back to the math transformer. So what we did here is we trained this transformer, François, I should say, trained the transformer on 300,000 samples. And then we generated from this transformer, which had learned quite well, we generated more samples. And we saw that they don't help over, even though we have many, many, many more, like millions. You can see that when it was trained on original data, that's the bottom graph, it learned all these nice skills. And when it trained on synthetic data, it just stopped learning these skills. It just learned a few and then that's it. Nothing helped anymore. Not that surprising if you think of it in terms of the zip flow and not ever seeing kind of these tails, but it's nice that the math transformer does that, and this is a word of warning here to our math friends to be a little bit careful when applying AI models to generate more data to train other models, basically. All right.
I'm sorry, so this data do not follow the zip flow of this synthetic data?
No, because as I showed you, we train on 300,000 samples, right? It learns something, but not much of the tail, and then it cuts off these tails as in the previous, for some reason. Okay, and then here is also the learning curve of François' transformer, and you see that when you have synthetic data, it ceases to learn. This is accuracy, but all these things corroborate the story that the scaling laws will cease to hold. We did this mathematical exercise of showing what happens when you do this multiple times. So we only showed what happens when you do it once. But when you do it multiple times, what you will see is as you repeat this process of regeneration and retraining n times, you'll get a decay of these scaling laws that goes linearly with n. So in general, we proved this in many, many settings. When you do this repetitive retraining, you'll get the normal test error and then n times something new. All right.
Can I
Yes.
So when you do this repetitive task, do you do it from the beginning or do you keep the previous training?
We do it from the beginning. I mean, here for these things, we start again. We start again.
Simply the synthetic data.
Yeah.
You forget about all the...
Yeah, I mean, there are all kinds of variants, and Francois did many, many experiments in the math and so on, but these ones show basically you have to restart. These lines there, you see how it kind of gets worse. All right, so what did we do with these, to show these just to the experiments, so you see how these kind of experiments are done? We took this Wikipedia data, we split it into chunks, and then we used 3/4 of this Wikipedia text and asked the model to finish this text, the last quarter, okay? And we trained it on text where we just had the whole text and we said, here's your first 3/4, here's how the last quarter should look like. And we train it in the fashion that Amaury has so nicely explained. And then when we generate, we still give it kind of original 3/4 of normal text. And then we ask it, now generate us the last quarter. And then we stitch this together and use this as the next AI training data for the next model, and so on. Okay, so these are the experiments we did with Llama, and these kind of again show how the perplexity, how kind of the diversity also in some sense decays when we do this again. Let me skip this just to show that when you have this several times, you see this, and you also incorporate finite sampling bias and kind of top P inference, etc. The scaling laws will, in theory, start looking like this rather than the line down. And even for Llama, you can see that we get this. This is a log scale, right? So we get this degradation over generations in these experiments. Okay, so this was the first scenario, which was kind of pure from the mathematical sense, is what if you retrain on AI synthesized data? Now the question is, what if you mix, which is a more realistic scenario? What if you have some real data and some AI data? And again, our theory can model this. And what we get is some sort of interesting grokking phenomena. So what happens is that, for instance, here the model will learn. Again, these are the scaling laws. This line, the kind of diagonal line, is how it should be on original data. And when you have this mixed data mixed around in a random fashion, it will first learn, then it will stop to learn, plateau for a long time, and then learn again. Okay, these are the effects when you look at this infinite memory model of mixing real data and AI data. So the point here is for the practitioner, usually when people say something plateaus, they stop training. And they say, okay, well, I've trained as much as I can. So the point is with this AI data, it becomes treacherous because there's something in the mix. You might have to wait for a while and then you will get more improvement. So this is just what comes out of the theory. What else? Oh, benefits of AI data. So remember I mentioned all these anecdotal evidence that said, oh, I used the diffusion model to improve my classifier, etc. So we can, theoretically analyze this scenario and we can show that if we have very little real data for our model and we want to use synthetic data, there are regimes, but they're only kind of mild regimes where the synthetic data will help for a while. Basically is if my real data is so few that I can only get to some extent into the tail, and my synthetic data from another machine or whatever has more tail, even though it's synthesized, right? In that regime, I will get a benefit from the synthetic data. So this is just translating the point of saying, if my synthetic model was trained on a lot of data and I only have very little data, then it could be good to even use outputs of a synthetic generator. But the moment this balance changes, we lose this advantage. Does it make sense? So this is just to explain all these papers, or a lot of these papers that claim benefits of AI data in various settings. We did, so this is the math piece. So for us, it was more, the LLMs were a nice occasion to do some nice math. So we kind of abstracted this model collapse phenomenon and analyzed it in the case of linear regression, kernel-rich regression, I should say. And because it gives rise to nice new phenomena. So we can actually, just do a mathematical analysis of a linear classifier on Gaussian data. It was in fact rich regression, it wasn't even a classifier, it was literally just linear regression on data, where we assume there's data with some noise. We classify this data, and then we use this classifier to generate new labels. So color here, yellow or blue, are the labels, but it's a regression, right? So I'm just making this a little bit imprecise, right? And we learn something, generate with this new generator, learn again, generate with this new generator, and we can kind of study this phenomenon of model collapse. And it gives rise to, for the mathematicians among you, it gives rise to beautiful new math that you can do in this setting that people haven't done yet, beautiful new effects. So here is, again, I'm regenerating, and you can see then what happens when you have the original data and the regenerated data many times, and you can really quantify what gets misclassified and so on. It gives rise to very nice new effects. Let's see. Of course, you always test with the ground truth labels. And you get similar scaling laws as I showed. So when you do this n times, you get a degradation that scales with the number of generations, for instance. And you can also study this in a case of Gaussians with a power law spectrum, which is often used to kind of model the feature space of a neural net. And when you do this, you see that things also shift, scaling laws change, things disappear. I don't think I want to spend too much more time on this, except of showing a few pictures, but somehow this thing doesn't work. Oh, here are the pictures, but that's not the one I wanted to show. Here. So here you see this kind of degradation again of the power law. In this case, the lighter ones are the good ones, the original data. And as it gets darker, you see the degradation of test error with data, with regularization and with sample size. You see all these effects that we saw in the wild. You can find them in this, for some reason. You can also find them in the kernel ridge regression. And in particular, there's one effect. People always regularize, and they find optimal regularization. And this also changes when you have synthetic data. And in particular, regularization often translates to stopping time. If you there are ways to kind of view one as the other. And this also means here that we have to change when we stop our training before we overfit. All this to say is that there is nice and rich mathematics that can be done, and there's more of it to be done in this setting. All right, so where does this leave us? Let me first be pessimistic and then be a little bit more optimistic. So the pessimistic view is that if we don't do anything and we just have language models, image models inundate our training corpora for the next model, scaling will disappear. And in fact, even we will unlearn. I mean, there's this collapse phenomenon. We'll not only not be better, we'll actually be worse in the models, right? Skills are unlearned. There can all be all these weird effects where things stagnate. And AI data can only help when real training data is scarce. But in general, things are not great. However, there are also new opportunities here, because all we need to do is we need to look at the synthetic data a little more carefully and not use all of it indiscriminately, I think. That's the message. And there are now new opportunities to do some sort of data curation or selection. And this is where, this slide was really literally made this morning because we had the deadline yesterday that Amaury mentioned. But here is an experiment that we did, again, with the help of François, to show this effect. And let me explain it a little bit, because it might relate to what Amaury said in some ways. So here it's a slightly different problem, not GCD. Here we generated matrices with random entries, 5 by 5 matrices. The entries were actually between -10 and 10. And we want to compute the eigenvalues of this matrix. Now, admittedly, this is not a hard problem like Lyapunov, but it is something where we can see what a transformer can do. So we did this with the transformer model. We want to predict the 5 eigenvalues of a 5 by 5 matrix generated in this random way. And here's what we did. So we trained on 200 such data points. X is the matrix, Y is the 5 eigenvalues, sorry. And when we train a model on these data points, François, a 2-layer nice transformer, gets an accuracy of 67%. Now, what is accuracy? What we do is we look at the 5 eigenvalues and we do some sort of L1 distance, but weighted by the size of the eigenvalue. Okay, so some reasonable metric to measure how well we have computed these 5 eigenvalues. Okay, so we do like percent, how are we within 2% of some reasonable metric? If we are, we declare victory, and if we're not, we say we failed. And that's how we measure our accuracy. So this transformer trained on these 200,000 data points gets an accuracy of about 2/3. 2 out of 3, it gets roughly right, up to 2%. Okay, so that's nice. And now and we know also that, I think we verified this, if we take this transformer and have it generate new data, and then just train another transformer on it, we'll get this model collapse phenomenon, it will get worse, etc., etc. That's not my point. My point is that here, we can try to do a triage of the data, the synthetic data. Some is good, some is bad, maybe. And we can use a verifier. So now this might be relevant for, especially for a problem like Llama2, where it's easy to check and hard to generate. Now, I admit eigenvalues are not exactly that problem, but let's assume it is. So then what does a verifier do? The verifier checks one of these 12 million, it gets this proposed solution for the eigenvectors, and it says, oh, it's good if it passes a 1% threshold. And otherwise it says, let's throw it out. Okay? So let's assume that's cheap to implement. And if we do this, and it passes this threshold, and about 1 in 5 pass that threshold, and then we train a new model on these, whatever is remaining of these 12 million, so 20% of that, so whatever, 2.4 million data points, what will happen is that the accuracy, the same accuracy as we measured there, increases to 95%. Okay, so we called this paper, Scaling Up with Synthesized Data Requires Reinforcement. And I think that gives the message, which I had on the slide, but it's not there anymore. There. So the point here is that maybe synthetic data, even for math, might be useful as long as we have a cheap verifier. Because then we can pick the solutions that are actually good, in this setting at least. Okay, and you have to see whether this setting matches whatever problem you have and in your scarce data setting. And once you can pick, then you can actually bootstrap yourself out of this, out of this deadly situation where you would collapse with little data, generated data to get good performance. And this is more or less all I had to say. Let's see if I have... Yes, so I guess the last bit of message that I have is here on this slide. If you just come back to the scenario where GPT just invades the training corpora and just all the text is GPT generated, you better be careful, right? And so what ways are there to be careful? Of course, there are now ways to distinguish GPT text from real text, and there's more and more of this. And there are all kinds of tricks. GPT itself thinks that its own text is particularly good. So then you can use this to figure out that it's GPT. No, seriously, this is how these methods usually work. There's also watermarking. Of course, you can hope that some people will just put some sort of, statistical signals in the text that will allow us to distinguish them and throw them out. Okay, so this might become more important as we face this kind of synthetic data age, as I was saying. But in any case, we have to reckon with this fact and see, what we do with this. And I think, this actually works. Thank you very much.
Questions?
I have one question. For the very first slide, very last slide, you said that basically if we keep using the data that we generated to continue to train the model, there is a collapse. But that's taking the human out of the equation. It means that when you generate data, then you repost what you like or what is good or this kind of thing. So actually the person that's going to use ChatGPT or whatever will actually sort what is good and what is bad.
This is a very good point, and this relates a little bit to this slide. So of course, the data that's put on the web is perhaps what you were saying, it is curated in some weird sense. Except we don't know if it's curated in the way that increases the tailness of data. Right? This is something we don't know.
You said that if we go further, do you think that actually if humans keep consuming this data, we actually ourselves get used to a certain get more narrower distribution of what we think?
As human, are you saying if a human acts like a model trained on its own data and we get dumber and dumber? Is that what you're asking?
Yeah, kind of.
I mean, human psychology is a bit beyond the realm of my competence, so I don't know.
Okay, the human sorts that, but actually if the human consumes what ChatGPT is giving on the ChatGPT as a narrow distribution, then it's kind of bad loop, but
yeah, I hear what you're saying. I'm an optimist in life, so I hope it's not going to happen. But there's another point that you made, and that's important. You might have heard that most language models are first trained on all this data, and then they undergo something called RLHF. And what that stands for is reinforcement learning with human feedback. So there's an H there, a human in the loop. And this is actually, when I said this is our paper, this is just one little piece of our paper. What we show is if there is a feedback loop where a human only has to choose. He only has to say, this is better than this. So let's assume the language model produces two propositions and says, do you want this text or this text? And all the human has to do is to pick the better one. In this case, it's the verifier. Here we did a slightly different scenario, but we did that too, where there are two proposed solutions, the verifier picks the best one. In that case, we can show in a theoretical setting that we achieve the same accuracy as if it was trained on clean data.
But regarding that, if you ask a human which answer is better, maybe the human will choose the one that makes him think less. So for example, if there is an elaborate solution and a simple solution, you're going to choose the simple solution because for him it's more
right. I think so when RLHF is used, I don't think we're yet in this very subtle phase. It's literally, is this text a better summary than this text? And humans tend to, it's cheaper to rank things than it is to produce a summary yourself. And what we show in this paper in a theoretical setting, again with Gaussians, etc., is that it's as effective. Picking is as effective as generating yourself, okay, in some idealized setting. Yes.
So I have a very related question. Now, when human choose in RLHF, for instance, from a good summary and a less good summary, then could be that synthetic data will be probably better summary, and then could it be that we lost, so we're converging to something that's only better summary, but we lose some of the bad summaries that were getting some data?
Yeah, so you're asking this, there is a whole another, so first there is the theoretical models where we just don't even think of, you're adding another dimension, which is diversity. I just want one dimension, which is good and bad. But of course, in the real world, there is this diversity, there's lots of work on this diversity trade-off in language models, etc., and then it relates to exploration versus exploitation in some sense, right? Because maybe it's worse, but it has more tail, etc. It's hard to quantify. Again, this is a little bit in its infancy. There are works that there's one paper, a very nice paper, the curious decline of linguistic diversity with regeneration, etc. So ideally, when we curate data, we'll have to keep both axes in our consideration. But this is all in its infancy in some sense, because we're only now facing this situation where it matters as training corpora for the next. So I don't have a good answer, but people are aware that there are more than one dimension. That's true.
So essentially, the moral of the story will be using synthetic data that might either overrepresent or keep the tails.
Yeah, I mean, in this setting, yes, right, yes, I guess.
Yeah. So is there something in the statistics of the synthetic data that can separate them? So if I have to use that, so I can say that something is produced by ChatGPT or is human.
Yeah. So as I said, the best.
Is that the best
detector to figure out whether ChatGPT generated data is to ask ChatGPT, do you like this data or not?
This is the best.
Okay, no, so the best, I just went to talks on this at the conference last, so I guess I can tell you what is the best variance of this. So where you make GPT infer the prompt that generated this data, and then if it after this prompt generates a similar data, then it was this kind of variance. But yeah, that's basically the best to figure out if it was synthetically generated by the model, more or less.
So there's no statistics you can do, which is...
I mean, this is some sort of very elaborate black box type of statistics in the Amaury sense of black box finding the answer. Is there a simple frequentist thing? You count the bigrams and so on? I'm not sure. There might be, but I think that one has that. It's not that obvious. It's not just counting how many co-occurrences there are. It's a bit beyond that. Yes.
I'm just curious that whether this verifier extends across different models, whether you can use ChatGPT to...
Yeah, so again, this is only one piece of the paper where we did the math because I wanted to please this audience, but we did experiments with, I'm blanking now, with Llama and news summarization, where there is something called the Rouge score, which kind of measures whether it's a good summary or not once you have the ground truth. You following? So this Rouge score tells us, it's like a verifier. And then we show with these Llama experiments, which again takes many weeks to run, that indeed when you use this Rouge as a verifier, you also get improvements. if that's what you're asking. So the verifier can come in various, it doesn't have to be a human always. It can also be a stronger model. We show in theory that as long as the model is much stronger, right? We show that in theory with our linear models with Gaussians. If you have a verifier, it doesn't have to be the ground truth, doesn't have to be the human, but it's kind of better than the current model. It can also bootstrap the data, to improve the performance. There are all kinds of scenarios that you can look at there. And often, by the way, lots of papers use GPT-4 to improve some other model. I mean, this happens all the time because GPT-4 is actually a very strong model. Yeah. Yes.
About the zipflow and mathematical data, maybe the question about the first token. So, for example, this Lyapunov function, for example, the polynomial. As far as for polynomials, we should not expect something like a zipflow. It should be more homogeneous.
Right.
But in some kind of, if it's not a zipflow of data, do we expect some of these scaling laws?
So I was a bit sloppy when I said you need zip to have scaling law. For instance, in our linear models, the ones that I showed you there quickly running, before we put a power law on the spectra, these were just, say, isotropic Gaussians. They also don't have a power law in that sense, but you get a scaling that is 1 over t, 1 over the data. So that's a scaling. So when I talk to Markus Hatter, he says that's not a scaling law because scaling law only comes from zip. But of course, there is a scaling inverse with the data set size that just comes from normal distributions. And this one is perhaps also the one that can be leveraged in these when you don't have a zip in math. I don't know if your Lyapunovs have any zips, I cannot say. I do not even know the eigenvalue, frankly. I haven't thought this through, if there is a zip or not. We need to think, the paper was written too fast. But there is scaling law and scaling law in that sense, if you wish. I'm not sure this is a helpful answer. But 1 over t doesn't count for them, but it is a scaling with t, if you wish. T is the number of data. Right. Yes, sorry. Did you want to say, François?
No, just for eigenvalues, there are. If you look at random matrix theories, there are many laws that you could exploit to say that some distribution of eigenvalues or some eigenvalues will be less common than others. You got those concentration inequalities that say that eigenvalues of a random matrix need to be far apart from each other. So if you have a matrix with close apart things, then it's a rare occurrence, then it's a tail, and so on. So you always have kind of a biased law that you can leverage. I mean, I don't think there are many cases where everything is uniform and you have no tails.
But for example, for polynomials, for example, a Lyapunov function, which polynomial should be kind of uniform, no?
That's a complicated. That's a good question. So what is it sampling uniformly a system?
Yeah.
When you're looking at infinite dimensional spaces, it doesn't have a discrete place.
Is there any way of finding the algorithm by which the machine finds the eigenvalues? I mean,
how does the transformer do it? Can we interpret? So this is, again, this should go to François. I believe that one is pretty large, millions of parameters. Is that what it was?
No, they're actually smaller than.
They're smaller than the GCD.
No, the thing is that in that case it's relatively impossible to see what the model is doing because there are way too many parameters. The only case where I can basically, for now in math, the only case where I can understand a case like GCD because it's discrete, got tons of theory and all that.
Learning linear regression, there's been a lot of work on understanding the algorithms that they learn from linear regression, which is not unrelated to the matrix problem.
That is true, although that's from the context rather than it's more here. We just give it one. I mean, the context is one. Yeah.
People do train ab initio on linear regression problems, and then the point is to learn to solve a new linear regression problem.
Yeah, right. But the whole, I see what you're saying. But the whole regression is given in one long prompt, like A B A B A B A B, like various.
That's right. A new instance of regression is given. It involves matrix operation implicitly.
So in this case, for example, for the GCD, I think at some point you mentioned that it does well up to 120. Is there any sense of, if we understand the method by which it finds the GCD?
Yes.
Why would
this I will present this afternoon.
Okay.
Yeah. So I don't want to. So the GCD one is somewhat amenable to interpretation, but as you also learned from Amaury, generally these black boxes are a beast. It's near impossible to get something out of them.
More questions?
Can I ask the last one?
I just have a question about the part where we mix synthetic data and real data, and we have this plateau of the loss before it decreases again. Maybe I missed something, but can you give me some intuition on why we have this phenomenon?
You know, I've been asked this question already, and I have to admit, this sharp thing only happens in the infinite memory model. And there I have to think, why is it happening? Let me think this through. But let me just, a disclaimer is once you get more realistic models that are not when we have other models that we can analyze, but they're not the infinite memory model in that strict sense, that doesn't become so sharp, it becomes like an S-like curve. So we just have some remnant of this. It doesn't answer your question. So why does it grok? Yunchen, do you have? I remember we were thinking, I'll think it through and try to get back to you. I'm a little bit dead still.
Let's thank